The last part of Unit 5, Notes 5.3, deal with molecular polarity and solubility. So, molecular polarity. First of all, what we want to recognize is that molecular polarity, or the polarity of an entire molecule, is determined by symmetry. Okay, so we are going to be looking at the overall shape of the molecule and deciding is the molecule symmetrical or asymmetrical to decide if the molecule is polar or nonpolar. Okay, in the past, we have talked about polar and nonpolar bonds, and recall polar and nonpolar bonds were determined based on the difference in electronegativity. But when we talk about the molecule as a whole, the polarity of an entire molecule is going to be determined by the symmetry. Okay, is it symmetrical or not? Polar molecules, then, are molecules that are asymmetrical. Okay, so this prefix A here means without. So essentially we are talking about molecules that do not have symmetry or are not symmetrical. Okay, sometimes it can be difficult, especially in 2D, when we draw these pictures, to decide if a molecule is symmetrical or not. And so what we really want to take a look at is the lone pairs of electrons. Okay, so most polar molecules are going to have at least one lone pair of electrons, and I should clarify here, that are found on the central atom. Okay, so the atom at the center of our molecule. If there is a pair of lone pairs on that electron or on that atom, then usually that's a good indication that we are dealing with a polar molecule. Okay, it is important to note that polar molecules could have nonpolar bonds. So if we looked at the difference in electronegativity, the difference could be small enough that they are sharing the electrons equally, therefore they have nonpolar bonds. However, the overall polarity can be polar based on the symmetry. Okay, so an example of a very common polar molecule is H2O. If I were to draw, and hopefully we're getting pretty good at Lewis structures for H2O, we would end up with a molecule that looks like this. Okay, once again, when I look at this, it is going to appear as though maybe it's a symmetrical molecule because it's drawn in the 2D. However, if I were to look at it in the 3D, we would see that the shape changes a little. And so what we're really looking at here are the presence of those lone pairs. And we have a pair of lone pairs here and a pair of lone pairs here. And so this is going to be an asymmetrical molecule or a polar molecule. Okay, so polar molecules are asymmetrical, and most of them are going to have at least one lone pair of electrons on that central atom. Nonpolar molecules, then, are going to be molecules which are symmetrical, meaning if we were to look at the central atom, if we were going to cut it any way, whether it's down the x, y, or z axis, both sides of that molecule would be the same. Okay, once again, sometimes this can be hard to see, especially in the 2D. So we're going to once again focus on this idea of lone pairs of electrons, and nonpolar molecules do not contain lone pairs of electrons on the central atom. And just a side note, most nonpolar molecules are also going to have nonpolar bonds. Okay, so a very common nonpolar molecule is carbon dioxide. We talked about this. This is a molecule that's going to have some double bonds. And so if I were to draw the Lewis structure for carbon dioxide, I would end up with this. Okay, once again, we're focusing in on that central atom, and this carbon has two bonds on each side coming out of it for a total of 4 bonds. There are no lone pairs on the central atom, and so therefore we would classify CO2 as a nonpolar molecule. Okay, let's do 2 more examples. Let's say we wanted to draw CCl4. Okay, if we draw CCl4, our Lewis structure is going to look like this. We're going to fill in my electrons. Okay, and when I take a look at my central atom, there are no lone pairs on the central atom. This is a symmetrical molecule, and so CCl4 would be classified as nonpolar. Okay, if I were to draw NH3, I would see NH3 looks like this. Okay, NH3 does indeed have a set of lone pairs on that central atom, and therefore it is asymmetrical, and so this is going to be a polar molecule. So again, if you can properly draw the Lewis structure, determining if it's polar or nonpolar isn't all that difficult. We're just focusing in on that central atom and are there lone pairs or not. Okay, so why is this important? Well, the shape of a molecule, the polarity of a molecule is important because it can help us determine some of the properties of the various atoms or various molecules. So in the next part, we're going to be taking a look at one of those properties. Specifically, we're going to be looking at something known as solubility. So solubility is defined as the ability of a substance to dissolve in a solvent. Okay, so if we think about Kool-Aid and sugar being mixed with water, okay, we would say that the Kool-Aid and the sugar are soluble in the solvent, which is the water, because we can mix them fully and they would dissolve. Okay, similar to solubility is this idea of miscibility. Miscibility is just referring to two liquids that will mix fully. So it's very similar to solubility, except we're talking about liquid. Solubility, typically we're talking about a solid in a liquid. Miscibility, we're talking about two liquids that mix fully. So the solubility rule that we want to focus on here, or the phrase we want to think about, is this phrase like dissolves like. The phrase like dissolves like refers to the molecular polarity. And what that phrase means is that a polar molecule is going to dissolve in another polar molecule. Okay, so for example, if I had two polar molecules, something like water and maybe nitrogen trihydride, both are polar, we would expect those two things to dissolve in one another. Okay, if I had two nonpolar molecules, okay, we would expect those two things to mix completely, as long as both of them were nonpolar. However, polar molecules are not going to dissolve in nonpolar molecules. And a very easy example of that is this idea of oil and water. Oil is a nonpolar molecule. We've already established from the previous slide that water is a polar molecule, and so we know that oil and water don't mix. Okay, if we think of Italian dressing, if we were to mix it up, it would mix for a little while, but eventually they would separate out. Okay, another side note is that ionic compounds typically dissolve in in polar molecules. Okay, so if we think back to the previous slide, the two that we drew water, H2O, which we said was a polar molecule, and we drew CCl4, which we said was nonpolar. Okay, these two substances we would expect to not mix in one another. Okay, so water and CCl4 would not mix. We would say they are not soluble or they are insoluble in one another.